Yeah, good evening, everyone. As so many EC graduates are interested in VLSI, but they don't know what are all the paths they need to choose and what are all the paths they really exist. So here I'm making this video to give a overall picture about what are all the different domains that are available in VLSI field, and also what are all the tools you need to go through, and also just like what is the output you'll get in every stage, and what is the design flow also. I'll going to explain a few things about VLSI. My main focus is on the domains of VLSI, how many domains are there, in each domain what you need to do. All those things we will discuss today, right? Then the first things first, right? Mm, yes. What is a VLSI? Okay. Simply we call it as VLSI, but it is a very large scale integration. So what is a very large scale integration? Now you have watching the NVIDIA CEO's presentations, and also you have watching so many other tech guys presentation, or it may be TED Talks, something. So wherever you go, you are watching about this large scale of integration of transistors. See, somewhere some people will say we have a we have made a chip of 230 million transistor, which may be of this size. Okay, so it's such chips to make. So whenever you are making such chips actually, how the things will go on. Okay, so how the process of embedding thousands of billions of transistor in a single silicon chip. Okay, so though it is in performance wise, or it is in the reduction in size, or it may be or it may be for the low power consumption of electronics. So how the things are designed. Okay, so during that designing, how many steps are there? So each step, what they will do. So as a EC graduate or someone who is aspiring to be a VLSI engineer, what are all the key skills you need to learn to make that domain as your career objective? Okay. So without wasting any time, let me jump onto the VLSI design flow. See, in the VLSI design flow, we have known this. Okay, because most of our textbooks, though it may be the Bucknell textbook, which usually the EC people study during their third year or fourth year in the as a part of their academic work, or it may be the aspirants who study the other books other than Bucknell. So there are so many online resources also where you will get sophisticated explanation on all these steps. But this picture actually I downloaded it from a random source on internet. Okay, usually whenever a client comes to you, whenever you want to design some chip, what happens? The first things first, you need to get the specifications of the design. What are all the design you want to make, and uh, means what is the hardware, how to implement that logic which is given to you. Okay, all those things you need to decide. And once you are done with the specifications, you'll come to the architecture. That is what are all the building blocks, how many gates you want to use, what are all the blocks you will plan. And once you're done with the planning, you go to the RTL level design. See, in the RTL level design, you use some code. Okay, though it may be Verilog code or it may be VHDL code. To implement that block, you will use some kind of code. And then you will come to the functional verification. You have written the code. Okay, and once the coding is done, you need to verify whether the code which you have written is working perfectly or not. And then you need to go through the synthesis, though it may be the logic synthesis, logic verification. Most of the cases we do these things in one go. Okay, so there are different softwares to, to do the synthesis of the design you made. But yes, I'll go through them in the coming slides. So now, yeah, once you are done with the functional verifications, you'll go to the logic synthesis. And once you are done with the logic synthesis, you'll come to the physical design. Anyhow, for the physical design, I have kept another slide to explain in detail about the physical design, because I love physical design a lot. I'm very much I'm very much onto the what we call in physical design. Okay, and then once you're done with the physical verification, physical design, you will verify that design and you will close your timings and then tape out. You sign off it. Okay, once you are done, you will go to your chip. Will go to the fab stage, and once you're done with the fab stage, it will be packaged and it will be tested. We call it as post silicon test. So once we are done with everything, the chip is ready to go, right? Then, so as I have promised, I'll go in detail about the physical design. So here I am. See, when the input to the physical design is actually the gate level netlist. Okay, once you are done with the gate level netlist, what you do, you will be placing your blocks, your logic blocks on the wafer. Okay, you may call it as core. Okay, so you will do so many steps like blockwise placement. You do once you are done with the blockwise placement, you will keep some what we call diffusion capacitances between them to separate them. So many steps. Whenever you go through the physical design, you will understand what are all those things. And then once the placement is done, you will go to the CTS. Okay, that is what we call clock tree synthesis. Once you are done with the CTS, you'll check for the timing. Okay, how the thing is going on, and is there any timing violations or not. Okay, once you are done with your timing closures, then you will go to the global routing and also formal verification. Though it may be DRC or it may be LVS, it will be done. Okay, and then once you are done, again you will go to the post global routing timing analysis. Most of the times before that, before the global routing, we go for we have different types of STA. Okay, so we have graph based STA, and we have PBA also. So before global routing, we go for one, and after that we go for another, right? And once you're done with the post global timing analysis, yes, if it is meeting everything, you will go for the tape out. If it is not meeting, again you will go back to the logic synthesis, right? Then, right. So out of this, whatever the things that we have gone through in this design flow, I just with all the experience I have, with all the what we call post I see on every day, though it is LinkedIn or it is the other platforms. So I just have mentioned the things domain by domain. Just go through it. It may be useful for you, right? Domain number one. So number one, I have divided these things into like front end and back end. So the first thing is front end, RTL design and synthesis, where you need to program. Okay. So here the specifications are there with you. Okay. You need to translate, you need to convert these specifications into some code. Okay. Though it may be Verilog core or it may be VHDL code, you need to write some coding to the functionality which is described in the specifications. Okay, so you are implementing the chip logically over here. Okay, so this code will design the control logic or the data paths or the pipelining. Okay, so many things will be defined over here. Okay, so how to implement this? So throughout my video, I'll be mostly going through two tools, that is Synopsys and Cadence. Okay, because they are the market leaders. Synopsys is literally in the number one place in the market, and with a little difference, Cadence is at the number two place in the market. So they are the rulers of market. So I'm going through the Synopsys and Cadence only, right? Then, so to write the VHDL codes, either we can use the design compiler in the Synopsys, or we can go with Genus in Cadence. Okay, so to write this or to pursue a career in RTL design, one should be perfect in Verilog or VHDL. So mostly I recommend Verilog. Okay, and once you are done, you need to be good in FSMs, finite state machines, and then SDCs and synthesis reports. Okay, So what is the output of this step? Okay, so if you are from RTL design team, so you will generate a gate level netlist, and once you're done with the gate level netlist, you will pass this gate level netlist to the other team. Okay, so yes, what you're going to do in this step, so you will literally turn your idea into the digital logic. Number two, verification. See, verification is there in front end and back end. So many times we will verify our chip. Sometimes we verify for the functionality. Sometimes we verify for the timing. So many verifications we do. So here, domain 2 is verification. It is in front end. Okay. So what we do? So you have written the code. Okay. So you have given nice RTL for it. So now in this step, we will check whether the given RTL is behaving as it is intended. Okay, so it may be functional, or it may be formal, or it may be low power. So there may be so many checks we will do. Okay, so how do we check these things? So again, we need tools, right? So here we go with VCS tool, Xilium tool, or Questa tool. Okay, three tools depending upon the organization preference we will use. So key skills you need to master verification is that, or to get a job in verification domain, you need to know about UVM, SVA, and coverage driven. Okay, so these are not the skills, these are all the methodologies that you need to be master with to get into verification side. Okay, people call it as DV also, design verification. Okay, so what are all the outputs you will get over here? You will get the test benches. Okay, and also you're going to get what we call them, the bug reports also. Okay, so 70% of the chip development, yeah, this phase is very critical. I'm saying is the 65 to 70% of the chip development time is spent in this step. Okay, that is why digital verification DV engineers are very much what we call the market is fire for them. Okay, so yeah, what you do here, you will find and fix the bugs before the chip is built. So that is the motto of this verification. Now the third step, now you're done with the front end, you programmed it, and once you are done with the program, now you are you verified the functionality, okay, in terms of the low power and the behavior, right? Now here you come to generate the chip physically. Okay, in this step, what you're going to do is you will convert your whatever the netlist they have given, whatever the netlist that the RTL team has given. Okay, so which is verified by the DV team, is came to the PD team. Okay, you are in PD team now. So what is your task is to, your task is to convert this gate level netlist into a physical layout. Okay, so in PD, literally floor planning. Okay, and then we call it as PNR, placement and routing, and then CTS, class tree synthesis, and then routing. And once you are done, you need to do the sign off. Okay, sign off is timing closure. Okay, if it is cadence, you need to use Innovus for physical design. If it is in Synopsys, you need to use IC square. So people will call as ICC or IC square, whatever it may be. It is the tool from Synopsys. Okay, that is IC compiler. Okay, so the output of this step, the output of the physical design engineer is the GDS2 file. Okay, so this GDS2 file is given to the DFT team. That I'll tell you what is DFT team, what DFT team will do. But what is the output from this step? The GDS2 file. So what we are feeding to this step? The RTL. Okay, so which is verified by the DV. Now, moving on to the domain 4. The STA. Actually, the STA is a part of physical design. Okay, but because of the scope of it, because of the importance of it, it become a little more important. Okay, so what STA will do, it ensures the signals in the design will reach their destinations on time. Okay, I mean, what is our duty? Okay, so here you need to verify the setup time and the hold time. If there are any violations are there, you need to address them. Okay, you need to address the clock skew and clock jitter and other constraints like a crosstalk and all those things you need to address in this. Okay, the key tools we use here, if it is synopsis, we use prime time, and if it is cadence, we use tempus to verify the timing. Okay, so right, the importance of timing, everyone know, means if a chip fails in timing, it doesn't function reliably. Okay, so STA is very important before the tape out, and it is a part of physical design. Okay, but we do STA for multiple times during the building of chip. Okay, so yes, but whenever if you want to choose your career in STA, I always recommend you to go through some what we call some PD. Okay, and then you come back to the STA. If you do like that, you will have better understanding of the concepts, and you will have the better understanding why you are doing this step and how the steps are. I mean, what is the result of that step? Okay, now. So once you are done with your physical design and once your what we call GDS2 is ready. Okay, so right here it is another important step, that is DFT, design for testability. If somebody is pursuing MTech in VLSI, they have a separate subject for DFT. Okay, yeah, yes. What is our duty? So here you need to build, you are building a chip. Okay, that chip has to be testable. Okay, whether it is code or it is chip, whatever you build, it should be testable. Because whether you are writing a C code or you are writing a Java code or you are writing a Verilog code, it should be testable. If you are writing some code that is difficult to test, it will not give any yield. Okay, so it should be testable. So what is design for testability motto is that you need to make the chips that are testable after the fab, okay, after the fabrication. So that may include inserting scan chains for testing those internal nodes or generating the test patterns using ATPG, okay, and adding some built-in self-test circuits, that is BIST circuits inside the chip. Okay, so for that purpose, we use two tools, that is DFT compiler. DFT compiler is from Synopsys. It completely automates this DFT process. Okay, so yeah, and Mentor Tessent is from Mentor Graphics. Mentor Graphics is also a key player in VLSI market. Okay, so the output what we get is scan inserted netlist and test pattern. Okay, these are all the steps we have, and these are all the tools we have in DFT. So this is also one domain where you can, which has so much of potential in the future market. Now the sixth one, the analog and mixed signal, simply people will call it as AMS design. Okay, so this is also in fire in today's market, because most of the things are, I mean, is implemented. What we call the most of the real life devices are implemented using these chips. Okay, so that is why what is happening, this analog and the mixed signal design is also very much important, right? So what you do here, see, we know even if somebody is speaking, I need a mic to speak. Okay, which will convert my analog data into digital data. Though if you are listening this using a speaker, your digital data need to be converted to analog data. Okay, so yes, the op amps, the amplifiers, though it may be DACs or it may be ADCs, so many things you need to design in this, but a tough job as compared with the other things, because you need to see the things as per the frequency, how they will act according to the temperature we have, according to the frequency we have, because some things will function in some way at high frequency, will function in different way at low frequency. So that is why you need to be very careful with it. Okay. And then what are all the concepts you should look for when you are on IMS design? Number one, it is noise. Number two, it is gain. And then once you are done with the noise and gain, you can go for this layout matching and all, right? So for mixed signal design, most of the people will use ADS. ADS will Advanced Design Studio, that will give nice analysis. It will give S parameters. It will give the Smith charts. So many details we will get in ADS if you are looking for noise and gain, and or else simply the cadence virtuoso. Virtuoso is a great tool. People will prefer using the virtuoso for this mixed signal design, right? Then the whatever the topic we are discussing, so this like AMS, this is also a separate thing, the FPGA design. So you will be given a Vertex 9 board or an RTX board, okay, and then you are asked to implement some model on that FPGA. Okay, so it also comes to the front end section only. What is your role? Your role is to develop a prototype, a reprogrammable logic. Because why I'm saying reprogrammable? Because once, what is the real flow is that the logic is once implemented and tested on FPGA. Once you are done with the testing on FPGA, that logic will be sent to make a chip. Okay, it is like ASIC design. If it is done, if it is good on FPGA, we will build an ASIC using that design. Okay, so that is the reason I kept like prototyping the reprogrammable logic. So just like how we are implementing the RTL, here also we use Verilog or VHDL for designing the logic. Okay, whenever it is logic, we generally use Verilog or VHDL. Okay, so quads is one thing most of the students will use, and then Vivado is also another tool because most of these labs in BTech colleges are equipped with Vivado in today's world. Okay, and then yes, why we go for this step? I told you to test. Okay, most of the time we use these FPGAs in R&D. Okay, because whenever we want to test some design, we go with FPGA design. Okay, what is the output of this design is a this step is a bitstream file. Then yes, we have gone through what is RTL designing. So whatever the domain is specified, so far I have specified 7 or 8 types of domains. Okay, so it may be RTL design engineer, the programmer, or the verification engineer, or the physical design engineer. So there are many paths. Okay, according to the path, according to your interested area, you need to choose your tools and you need to get into the thing. Okay, so right, what I'm saying is, if you are an RTL, if you want to become an RTL design engineer, you need to master the Verilog coding. So you don't need to look at what we call the physical design engine, all those things. Okay, the backend part you don't need. Maybe the basics is required. So, but most of your work will be on Verilog, right? So you need to concentrate. You need to focus more on Verilog only. Okay, so likewise, I have mentioned 7 different types of domains, which will lead you to 7 different career paths, especially in VLSI, right? Then how to prepare? Right, though whatever the path it is, okay, though it is the physical design or it is though it is back end or it is front end, the one must be very good with the flip-flops and the FSMs, okay, the Mealy and Murray machines, all those things. You need to strengthen your digital electronics fundamentals. Okay, you should be good at flip-flops. Okay, how what is a flip-flop, how the clocking schema will work, how the clock will affect the output, how the timing violations will affect the output, everything. You need to be very perfect in digital electronic. Once you are done with that, you can use your HDLs. Okay, it may be the Verilog or it may be the VHDL, but most of the people will use Verilog only. Okay, you master it. Okay, and then you understand the flow. Okay, or you can choose the tools. So you may ask me, Sharat, you are telling all synopsis and cadence tools. Where from we get this synopsis and cadence tools? Okay, so in that case, you can go for this open source tools. We have open source tools like Yosis for implementation, and then OpenSTA for timing verification, and Magic Tool for physical design. Okay, these are all open source tools. Though these tools may not be powerful as such as licensed tools, but they will really help you to understand the key concepts and how the system is working. Okay, how the system is working, how the flow is going on, all those things uh, you can understand in a better way. Okay, then I told you 7 disciplines I explained, so it is a very big interdisciplinary field. It is not one team. I told you the RTL team will give the RTL team output will be the input for DV team. The DV team input output will be the input per PD team. So it offers. We have multiple disciplines in this field. Okay, so it may be digital. See, there is a conception in people that people will build digital chips. I mean, this binary things only in VLSI. It is not like that. I told you, people can design amplifiers, people can design op amps, people can design ADCs and DACs. Okay, so yes, if you are interested in analog side, you can go for analog mixed signal design, or if you are interested in other side, you can choose it. Okay, so yeah, that is the fundamentals, and that are all the tools that you need to work out to have a proper career in VLSI, right? So yes, if you do have any doubts, you can keep it in the comment section. I'll answer them whenever I am free. Okay, so the response may be delayed, but it will definitely come, right? Thank you. Thanks for the time, right? Yeah, all the best.